Okay, so hi all, and in this this will be our last video, I guess, of the semester, since I'll wrap up with the material here, which is mostly just I don't have any new material, just really me doing one more example to show you kind of one last little thing here. I'll so let's do that first, and then I'll give you some final words, I guess, about our plan for next week and exam and all that good stuff. So, so I think this is our topic really of the week here is revisiting the spring problems, and in particular revisiting them with this extra force added in, this external force, F of t, that is. We've been using mostly the impulse, the newfound things that we learned about the impulse and step functions to represent this. But the idea, of course, right, is that in addition to the forces we talked about when we derived this model, we may have this additional external force, as it's usually called, which is just a way of saying something else, right? Some other thing is acting on the object hanging on the end of the spring. And the only thing to really take away is from this is just that what does that external force, which we're using big F of t for in this derivation here, where does that end up in the model? Is it just becomes the either left-hand side, or as we usually wrote these the other way around, more so the right-hand side, but it becomes the other side of just our standard homogeneous spring problem that we studied earlier, right, in the month. And so the only difference in terms of solving would be that you need to approach it as a non-homogeneous ODE, which, again, if it's if F of t, the big F of t over here, if this is a problem like ones that we might have done on the last exam, you could use those strategies. But of course, a lot of time, the big F of t is one of these new functions, this impulse or step, which we can't really do with our traditional method. So we would have to really use Laplace transforms to solve this, but we would want to anyway, right? Even if F of t wasn't one of those. So we did a few examples, right? And to sort of make sense, it's one thing to write down a model, and we sort of quote unquote derived it, I guess, but it's one thing to say, so this is how it should be, but it's another thing to see, does this actually agree with what we expect to happen in real life with something like this? So so we did I think we did two examples, and I'm just going to do one more for us here that kind of is a little more complicated. We looked at this first problem, which was a spring that had no initial movement of any sort, and had a step function at time 4 as its external force, and this has no damping. And so, not surprisingly, when we solved it, we got a bunch of stuff. But let's look at the graph briefly here. Not surprisingly, what ended up happening is that since there was nothing to set it into motion, it waited until the external force turned on, which was apparently at time 4. And then since there was no damping, it oscillated forever, right? This spring will just keep bouncing forever if there's no damping. Okay, so that was one possibility. Then we introduced damping, so this is the second example that we did, and this is what we stopped on last time. We add the damping, so damping, of course, means that it should slow down, right? The spring should come to rest in a normal situation at some point. And for this one, instead of a step function, we tried this impulse function. And remember, an impulse function is a quick hit, as opposed to a step function, which represents a prolonged force. An impulse function is a quick, sort of almost infinitely quick hit or punch, or for the spring, probably makes sense to say like a flick of your finger. So again, we did the same kind of setup of saying, what if there's nothing to start with, no movement to set this in motion, and instead we will wait. Remember, this is the notation we're using to say that the impulse happens at time 5. So if the flick doesn't happen until time 5, what should the solution look like? So we did a bunch of stuff down here, and we came up with a solution down here. But what did that solution look like? Well, again, not surprisingly, if there's no initial displacement and no initial velocity to set this in motion, then of course it's just going to be sitting there waiting until at time 5 you give it a flick. And we give it a positive flick, which actually is down, since this whole thing is upside down, but that's all right. I gave it a positive force, so that, of course, causes you to shoot up. But then there is damping. So as I oscillate, the amplitude is dying out because of resistance, right? Air resistance. Okay? So that makes sense, right? So that agrees with our human notion. I think I probably finished by saying this is probably a reasonable example of how, when we were kids anyway, we played with a spring, which was that we kind of let it hang out for a minute and then said, okay, after a while I'm going to give it a flick and see what happens, and it bounce, but it eventually came back to rest. All right, so I just wanted to do one more example, which I'm actually just going to recycle the one that was just on that last slide there, but I'm going to add the fact that we will set it into motion at time 0, just so that we can sort of see the full behavior of the spring problems. So let me write this down. So this, I think I'm up to 3 now. So example 3. All right, so this is the same setup. So consider the spring given by. So we'll use the same ODE so I can save a little bit of time on solving this. So let me copy it down though. So this is the ODE, and we'll even stick with the same impulse. So actually, this is the exact problem that we just did. But let's just make it a little more interesting here by saying that while there maybe will be no initial displacement, we will give it an initial velocity of, let's say, -3. Okay, so this is the same exact problem, right? That all of that's identical, actually, even up to and including that. The only thing I changed was this, right? So it's the same problem. I'm giving it a flick at time 5. It's a flick of force 12, right? So the coefficient, the impulse function by itself has a total force of 1. But of course, if I multiply that by 12, that's saying the total force is 12. Okay, whatever. That doesn't mean a whole lot to us just because this is not a physics class, so we're not getting too much into what that all means. But yes, technically that is the total force, or the total amount of force, which is really an integral. But anyway, but on the left-hand side here, this is the same ODE we just looked at. Of course, the only notable things here is that, yes, we do have damping. So we would expect there to be the resistance, air resistance, and so vibration should die out. Of course, this is a hit, right, or this is a flick at time 5. Well, that's going to do something. Now this, of course, says no initial displacement. So in other words, we're not pulling it down or compressing it up. But this, of course, is saying that when at time 0, we give it an initial velocity of -3, right? Which is up in our real world, but anyway, but it's a negative, right, initial velocity. So of course that should start when I start the process. I should, of course, see negative u values when I start this. Now I'll spoiler alert it that when we did the same problem but without that, we started with positive. I mean, it eventually rebounded to negative, right? But u was positive to begin with here because the force that we're flicking, right? We're flicking it with a positive force, which again technically is down. I know this upside down thing is a little bit annoying, right? But we're giving it a downward flick at time 5, but we're giving it an upward push at time 0. Okay, right. So think about, right? Think about, maybe make a little bit of a guess of what you think might be happening. But let's see, right? So let's solve this, and we'll see what happens here. Okay, so we'll just solve this as usual. So first things first, I'll do the transform. One thing I could do is probably, to make my life a little bit easier, is divide everything by 2 here. I think I did that last time, or if I didn't, I should have. So let me just divide everybody by 2. That'll make this all look a little nicer. Okay. So that's certainly legal, to just divide everybody by 2. Okay, now I'm ready to go. So I do the Laplace transform. I get s squared Laplace of y minus s times, I'm sorry, it's not y, it's u. S times u of 0, which is 0. But then minus u prime, that's minus negative 3. Okay, and then I have 4 Laplace of u's minus u of 0, that's just 0, so maybe I won't even write that down. And 13 Laplace of u's, that's from that one. And on the right, the coefficient always just comes along, so the 6 comes along, and then the delta function, or this impulse function, right, has an easy transform. It's just e to the negative 5s. Okay, so it's because the step, or I should say the impulse is happening at time 5. Okay, so that's my transform. So I finished the forward version. So let's see, in order to solve this, I'll do the usual, organize myself. So get the Laplace of u's on one side, so that's s squared, and oh, I'm sorry, I forgot an s here, didn't I? Sorry. For s Laplace of u. Sorry about that, right? The Laplace of u prime is s times Laplace of u. So, sorry. So 4s and 13. Now then, it turned out to be a positive 3 after all is said and done. I'm going to put that on the other side, so I'll leave that alone. And if I put it on the other side, my positive 3 on the left becomes a minus 3 on the right. Okay, and so now, of course, I'm going to make this read Laplace of u equals by dividing through by this. And so let's see, so I have 6 and e to the negative 5s. And that's over s squared plus 4s plus 13. And then this other term, I'm going to leave these separate. And I'll say why in a second. So, of course, we know our goal in the next step is to do the inverse of these now. So when you look at the chart, right, the e that we see here, and then, of course, here as well, of course, to do this, right, to do the inverse when you have an e, I mean, unless you just have the e thing or the e thing over s, you're going to have to use Rule 10. So now, I don't really want these commingled. In other words, you don't really want things that have e's with things that don't have e's. So I'd say it's always safe to say, don't try to sort of put those all in one fraction or something like that. Keep them separate, because of course the trick we're going to use on the e piece is going to be to say, is to use Rule 10, which is going to basically involve us sort of pulling the e out in front anyway, right? So, so I think you're probably better off just leaving the two fractions separate, and then we'll work on each of them separately. However, what we maybe notice here is that the bottoms are the same, and in fact the tops actually aren't even all that different from each other. So I think I'm going to have reasonable luck, I guess I should say, or success, being able to separate these things, and maybe I can even use the same trick on both of them. So let's see. So I'm just going to go to the next slide here, so I have enough space to finish this. So I have Laplace of u equals. So if I'm trying to make that first piece look like Rule 10, so coefficients for sure, I want to probably pull those in front. That's an always. I probably always, or more or less always want to do that. The E, I'm also going to pull in front, because to make it look like Rule 10, I'd sort of like to have the E and then the rest of it. So in order to make this look like Rule 10, I might start by saying, well, 6, that's just going to come along. Then you have the E piece, and then what's left then is 1 over s squared plus 4s plus 13. Okay, so it kind of helps to write it, or I think it kind of helps to write it like that. Okay, and then my other piece is minus 3 over 7. Okay, so I'm moving towards having this hopefully be correct for Rule 10 in the chart. So I would be all set. So the 6 will come along, the E would turn into a U, but I would have to deal with what's the inverse of this. And then I also have to do the shift, so don't forget about the shift. But notice this guy and this guy, right? In fact, even if I want to, I could, you don't necessarily have to do this, but if you really want to see how they are the same, you could say that. At which point, really all I need to do now is figure out how to deal with the inverse of what's in the parentheses, because it's actually the same in both pieces. So for that, I maybe come off to the side and say, oh, all right, so now here's where I don't want you to get confused, right? What's the difference? While these two are identical, and obviously we're going to be able to, in a minute, write down the inverse transform of this expression, I'm going to do slightly different things with it in my answer. So I don't want to confuse anybody here, but I am going to just say, so what I'm focused on right now is seeing if I could get the inverse of this. Right? Well, I'm going to go ahead and save us a little bit of trouble here, because we did this problem in the last example, right? So I'll just remind you. So let's see. Here it is. 1 over s squared plus 4s plus 13. That's a complete the square problem, which we did last time. So let me not torture us with this again. But this turns out to be the same as this, which you could, and then in order to get a 3 on top, I'll just do a little bit of doctoring. I have slightly different numbers here, but right. So I think I might end up just saying similarly, right? I think I might end up so I should complete the square, which let me fill that in first. Okay, so the bottom here turns into s plus 2 squared plus 9, or 3 squared if you want to write it that way. Okay, that's just completing the square. I don't want to redo it, right? But it's literally exactly the same thing. Complete the square that we did in the earlier problem. Okay, now this, let's see, is close to what you want in order to use, is it Rule 8, I think, in the chart? Or not 8, 6, I think. So it's close to Rule 6, but 6 would like a 3 on top. Okay, so that's all right. You can make that happen if you want a 3 on top, right? Because this is b squared 9. 9 is b squared, so obviously that means b is 3. So in order to fabricate a 3 on top, balance it by putting a 1/3 in front. Okay, so these are all the same. I don't know why I keep writing after this, but right, same. Okay, so now I'm in good shape in order, now I remember why, okay. So now I'm ready to say, this is perfect for rule number 6. Okay, so if I go backwards now, that turns into little f of t, coefficients come along, and rule number 6 read in reverse tells me that this is going to turn into e to the negative 2t sine of 3t. Okay? Now, so hopefully so far so good. So the question is, what am I going to do with this? And here's where I don't want to, like I said, I don't want to confuse anybody. So I think I've done everything I need to do, but when I come back to the left here now, I have to just think about how am I using this. So for sure I have figured out the inverse of this. So let me finish the right piece first. So I'm going to use just rule 6, right? I mean, or I've already done it off to the side here. When I go to the inverse, right, this is coefficients come along, and this turns into, via rule number 6, I'm just actually repeating what's over here. This turns into, right, 1/3 e to the negative 2t sine of 3t. Okay, because that's legit just exactly this problem. In fact, of course, you can see this was a little silly. I actually had the 3 that I needed up here a minute ago, but that's okay, right? Because when I put these together, the 3 and the 1/3 are going to cancel, so that's fine. But over here, you just have to be a little bit careful, right? So what rule am I using over here to go backwards? So, right, so of course I'm doing u equals. To go backwards here, I'm using rule 10, not rule 6. Now, I can recycle, so of course 6 comes along because it's a coefficient. Rule 10 says, of course this is telling me c is 5. And rule 10 in reverse says, okay, so the e piece might turn into the step function. Fine. But then, remember, this is supposed to be little f of t minus c. So this is where, don't get confused here. This is little f of t, because we worked on this piece, right? It was this, right? That's my big F of s. So I already did all the hard work, right? And I ended up with little f of t is this guy. But I'm not supposed to write that down. I'm supposed to write down little f of t minus 5. So I've got to make sure I remember to shift this answer by t minus 5. So I'm going to plug t minus 5 in for all of the t's. Sine of, I'm going to run out of space here. Sine of 3t minus 5. Okay. Okay, so we're using this twice. It's just that on this side it's shifted because you had the e. On this side there is no e, so it's not shifted. All right, which is actually going to be really important. So let me clean this up because this looks like a hot mess right now. So here's our solution. So let me simplify this a little bit. Stylistically, usually, I don't know why, but you usually put the thing that doesn't have the u in front. So I'm actually just going to do that just to, I don't know, to match what people normally do. So I'm going to pull this term in front. So here's negative 3 times 1/3. That's, of course, just negative 1. Right, so I really have negative e to the negative 2t sine of 3t. And then let's see, I have a little bit of simplifying here. That's 6. Everything is multiplied here, right? 6 times 1/3 is 2. So I think, and it's plus. Plus 2 u5 e to the negative 2t minus 5 sine of 3t minus 5. Okay, so that's my actual answer. Okay, so right. Oh, right. So reading this, let's just study it for a brief minute. Obviously, I'll draw you a graph of this as well. So there's a piece here that doesn't have a u, and then this piece, of course, has the u. And remember, of course, the u is just really an on-off switch. So up to time 5, this is blanked out. This is all just 0. So the graph, or the solution, up to time 5 is just this piece, the front piece. Now after time 5, this turns into a 1, and so you'd have both pieces. You'd have the shifted piece plus this initial piece. Okay? So what are these pieces? So let's just give a broad thought about this, and we don't have to think too hard. The trig, they both have a sine, and we know what sine does. Sine's an oscillator. But they also both have an E, And of course, it's e to the negative something. Right? They're both, the exponent's going to be negative for both of these, right? No matter what the t is. I guess I should say early on, right, when t is small enough, this would actually be positive. But again, remember, when t is less than 5, this is actually a 0. So it's blanked out. So it is true, right, that the exponent of e is always negative. And as t gets bigger, in both cases, as t gets bigger, it's causing the exponent to get big, but negative, which we know, of course, means it's going to make the whole thing go to 0. So none of this is surprising. We've looked at characters like this many, many times. This is an oscillator whose amplitude is shrinking as time goes on, right? So this is it's a that. And this one is too. Same thing. However, the fact that we have two pieces here, and in fact one of them has the step and the other one doesn't. This piece, of course, this is sort of turned on right from the get-go, right? So at time 0, this piece, or right after time 0 anyway, this piece is actually present, whereas of course this piece waits until time 5. So if I wanted to graph this, if you really wanted to punch it, you could punch this into your calculator and graph that up to time 5. And then after time 5, you'd have to graph the sum of this plus this. But I'll save you the trouble, right? If you wanted to do that, you could. But I'm going to abbreviate it on the next slide. I don't want to copy this over again, so I'm just going to say graph, right? So graph this. And I'll do it on the next slide here. So if you were to graph this, I'll give us a nice, decent-sized graph here. So that's time. What do we get? So up until time 5, this is off, so it's really just this, and that's just a regular old oscillator. Now sine, of course, heads up first, but since there's a negative, it's actually going to head down first. So this is just going to be a diminishing sign that starts at 0 and does something like this. The usual thing, right? 'Cause it starts off down, but then, damping takes over and it vanishes. Now at time 5, both pieces turn on. But let's just say, just very briefly here, at time 5, e to the negative 10, I don't know what that is, but I'm pretty sure it starts with 0.000000000000. Okay. So at time 5, this is essentially 0. So it's really the case that after time 5, it's pretty much just this. And now what is this? This is actually almost the same as, it's just a shifted version of this. The only difference is that this has a negative 1 in front, and this has a positive 2 in front. So the only difference that we would see between the first phase and the second phase is that rather than being multiplied by negative 1, which made it look like that, we'd multiply by positive 2, which is going to make it have a higher amplitude, and also make it go up first. And also probably make it have a little, I need a little more space. Probably have a little longer before it dies out. So this isn't, obviously this is not exact because I'm just sketching this. But this is probably pretty accurate actually, for at least in terms of a comparison of what this is. So let's do a little bit of, as we like to, discussion of this graph and make sure it agrees with our intuition about things. So first of all, note 1. We know we have damping in general, right? Throughout the whole process, right? What was it? 8, right? The damping coefficient is 8. So we have actually quite a bit of air resistance, right? So whatever this is that's bouncing around on the end of the spring, it's got a lot of surface area because it's dragging quite a bit. So we have damping throughout, so that explains here. So that explains why the oscillation dies out. groundbreaking. We already knew that. But what's a little more interesting, right, is that this graph, you might say, sort of has two phases. Here, this first piece, maybe instead of doing it at the bottom, well, I'll do a little bit of labeling up here, right? So this phase, this oscillation, this is due to the initial velocity, which was negative, by the way. Right? So this vibration that we see before time 5 is because you pushed it upwards, because it's actually negative, right? But you gave it an initial negative velocity, so you gave it a push. It's just sort of similar to a flick, right? Because again, the idea of an initial velocity is that it's instantaneous. It's not as though you're continuing to give force. It's just a quick hit in order to get it in motion. So in some sense, there's a similar kind of behavior. But in this case, the fact that it was negative means, of course, when you start the process from equilibrium, the displacement is negative at first. And then eventually the spring force pulls it back hard enough that it starts to head back towards equilibrium, and of course bounces a little bit over equilibrium onto the other side. But then the air resistance is killing this, and it levels out. Now all of that happens before time 5. Right? Because like I just said, if you plugged in, for example, time 4 even, I'm pretty sure that's a number that's 0.000, very small, right? Very close to 0. So that tells us, of course, that the initial velocity, while it did get it in motion, the damping very quickly killed that off. So then it sort of almost waits. I mean, it's probably vibrating ever so slightly. But then what happens at time 5? Well, somebody comes up and gives it a big flick, now in the positive direction, though, and that sets the whole thing in motion again. And that goes up for a little while and then comes back to equilibrium, rebounds the other side, comes back to equilibrium, but then again resistance takes over and eventually kills the vibration, and it heads towards 0. All right, so this first portion, I really should have done this in different colors. I'll draw a little line there. So this first portion is all due to the initial velocity, but then this entire second portion, this is all due to the positive impulse at time 5. All right. This apparently the strength, the amount of impulse was greater than the initial velocity, which kind of makes sense. Oops. These aren't quite the same units exactly, but this was 3 versus the force here was 12. It's not exactly a 1-for-1 thing, because of course this is like feet per second or meters per second, whereas this is newtons or pounds. But, okay, there's obviously a connection and a relation there. And evidently, the solution panned out, this force must have been a little stronger than the force due to this initial velocity, because we ended up getting a higher amplitude from the impulse versus the initial velocity, which only produced, a little bit of a shorter one. Which, again, I know I'm just eyeballing this, but it's also just because this is a 1 and that's a 2, right? That's what I mean, right? Right. Okay. So I'm not sure what else I should write down here, but okay. We have sort of 2. Vibration problems. Two vibration problems in one here, right? I said it up top, so I'm not going to repeat writing it down, right? One vibrational problem that's due to the initial velocity, then that sort of resets, and then here comes a big impulse at 5, which sets up another vibration problem, right? So you can imagine, right, real life systems, real life things that model or use vibrations, where there's maybe a periodic impulse happening. I'm thinking, bridges and things like that, where it's accustomed to having like almost like a schedule of impulses or regular things that happen repeatedly. This is at least a shout out to that, to say, yeah, sure, like these things vibrate and they reset. Then something else comes along and it vibrates and resets, and then something else. Right? Okay. So of course you could imagine problems where you model that this happens maybe every 5 seconds. There's yet another impulse. Right? Okay. So. But I think it's pretty good, right? I think it's pretty good to see that this. I know sometimes when we look at these answers, it's just like, ugh, what the heck is that? But try not to be too intimidated about thinking about it. Remember, the U is just an on-off switch, so that's helpful. And if you really want to punch these into a calculator and graph them, if you're not confident sketching, you can. Just make sure you do sort of a graph for pretending that this isn't here at all. That's up to time 5. And then after time 5, this is just a 1. And so then it's really just all that stuff after time 5. But I'm pretty confident that you get graph, at least look something like these, like this one that I sketched here for you. So, let me get out of here. So with that, I think we are done with ODEs. So, which is a happy moment, perhaps, or maybe not, but probably somewhat happy. I would say even I'm pretty happy, probably to be done with this crazy semester, or almost done anyway. So I'll just take 5 more minutes to just point to some things and to talk about the end of semester stuff. Of course, first and foremost, there's a WebAssign assignment. It's a bit of a longer one, so if you haven't already gotten started, please do so now. It's due on Monday, so check out the problems there. It's these impulse and step functions, and maybe it's just some other. I think there are some vibration problems. If they're not actual vibration problems, they're just they're ones that look like vibration problems, whether they're saying it's from a spring or otherwise. But anyway, have a look through and obviously give them a try, and hopefully those go all right. So those are due on Monday. On Monday, and this was, of course, was supposed to be final exam week. I don't want to torture you with doing more material, since at this point I'm sure you've had enough of this and all of your classes, and you're just doing the usual end of semester projects and exams and things to try to finish up. So next week, so Monday, you can take Monday and Wednesday to study and practice and do all of those usual good things at the end of the semester. Our exam is going to be on Friday, the 15th, which of course is the last day of the semester. So if you click on exam 3 in Canvas, you'll see the usual information here, at least for now. There are some review problems. I think it's quite a long list of review problems, or I guess I refer to it as an insane number of problems. I think I made these last semester because I ran out of time. Maybe we had more snow days or something last spring, but anyway, I sort of ran out of time, so I had to sort of give them a lot more practice problems. But we actually finished just fine. So anyway, feel free to check those out. Evidently, there's plenty there to keep you busy, and some solutions down below. So our exam on Friday is, of course, just on Laplace transform stuff. We did revisit spring problems here at the end, so I guess I should say, yes, you will probably have at least some spring interpretation to do, even though that was sort of from last unit. But anyway, obviously a focus on Laplace transforms, and using them. I will be asking you to solve the problems via Laplace transform, even though I know a lot of them you could solve them via other methods that we learned earlier in the semester, but I will ask you to be using and showing work for solving using Laplace. I'll try to make it such that they won't all be, here's an ODE, solve it with Laplace, because those can take a while, right? So remember, since for the most part the hard part is doing the inverse piece, I will almost surely have some questions that are just tell me the inverse transform of blah, 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 which means it's essentially you don't have to do the first couple of steps that you usually do. You're already at the point where it says Laplace of y equals stuff, and you just need to take that stuff and do the inverse, right? So switching from s's back to t's. So that's an easier way for me to test, are you good with the chart and doing the inverse and using the tricks and all that other good stuff. So anyway, so there'll be some of those, and then there will be some other, full ODE, solve this whole thing. And the usual, right? As you all know, I certainly like to ask you about where did certain things come from and whatnot, which are the questions that you all probably hate more than just the computational ones. I should say, of course, obviously you can use the chart, right, and have the chart in front of you. It's on Canvas. If you want to print one out so that you have that at your fingertips, that's not a bad idea. I will have you, I guess I shouldn't say definitely, but I may have you show some derivations of Laplace transforms from scratch. So obviously in the course of doing a problem, use the chart, but I may have derive one of the things from the chart. We did a few of those together when we were first starting with Laplace. So just, I guess I would say, be on the lookout that's a skill you should be able to do. So obviously keeping in mind that some of them are very, very hard to do by hand and others are not so hard to do by hand. So I shall try to make ones that, if I do ask you to do one, that is at least not too crazy for you to be able to complete. But just make sure when you go back through your notes, it was maybe the first lecture in this whole unit was where we were doing them by hand, just to sort of get a feel of what are these things and what's the domain of these functions. Why does s have to be positive or whatever it had to be for some of them and stuff like that. So so next week, right? So take all of next week, to study, to review. Of course, if you have questions when you're studying and reviewing or doing practice problems, feel free to get in touch with me and or a tutor. I'm obviously around all week. If you want to meet, we can Zoom, or if you have something smaller that you think I can answer in email, feel free to do that. And then our exam is of course Friday, so we'll do the same kind of thing that we've done for our last couple now, which is to have I'll post the file, and you can print it if you want, or just look at it on your screen and do it on blank paper. I think we've all gotten better with the whole scanning thing and uploading pages. So I think we've hit got a good skill set there with doing that. So you'll do the same thing. You'll upload your pages to a Canvas upload, and that way I'll have your exam and I'll grade it as usual and put it into Canvas, and you'll have your final exam or your final course average, which of course then translates into a course letter grade, right? Was I going to say something in there? I totally lost whatever it was I was going to say. So I'll hopefully have these graded over the weekend. We're meant to have our grades in by Monday, the whatever that is, 18th. So you should be able to, for all of your classes, see your course grades on by Monday, right? Just go into my Endicott, and you should be able to see our class and others. I guess I'll give the obligatory. There's no scaling or extra credit or make up assignments or anything like that. So hopefully, if you're looking for, I hope I go up a notch or whatever from where you're at right now with your grade. Then doing well on this exam is your best bet for that. This will go into the pot of exam, the exam pot of points, which I don't remember exactly what percentage that is. But this, like exam 1 and exam 2. So So you can do a little experimentation of what if I get a this or that, if that makes you happy. If you have switched over and are taking the class pass-fail, obviously you need to make sure that you get high enough score to at least pass the class. I think that's about it for general advice. I'll send you guys an email next week. Maybe not on Monday, but maybe more like Wednesday, just to say hello and remind you of the format for the test and all that other stuff. But you have everything on Canvas that you should need in order to study and get ready. So if you have any questions, please feel free to reach out either over the weekend or next week. And good luck studying, and we will chat next week.